What does Green's theorem say? Which I guess I should write in green. Green's theorem. Basically, the assumptions amount to you've got a vector field that's nice, that has continuous components that are also differentiable. Those derivatives have to be continuous. On some domain in the plane, containing a closed curve, oriented counterclockwise. So the arrow points counterclockwise. Green's theorem says that one way to integrate the vector field over the closed curve is to do a double integral of all things. A double integral of the scalar curl over the domain that's inside C. It's pretty amazing. Who would ever guess such a thing would be true? Well, evidently Green did. He guessed it and then he used it. Probably didn't prove it, I imagine. It's more of a scientist for one thing, and also just even mathematicians from 200 years ago didn't really prove things rigorously. Now, maybe from more like 250 years ago. They gave intuitive heuristic arguments instead of rigorous proofs. And if F is conservative on D, that implies the scalar curl is 0 on D, which implies the double integral of the scalar curl is 0, which implies the line integral of F around C is 0. i.e., the circulation is 0. In fact, if F is conservative on the entire plane, then it's conservative on any domain D, and the scalar curl is 0 on any domain D, and the circulation around any closed curve is 0. It doesn't mean the circulation around a piece of a closed curve is 0, or the circulation along a piece of a closed curve. But when you come back to where you start, you got to get 0. And that's because another way to see that is because the line integral is independent of path. If you end where you start, you got to get 0 by the fundamental theorem from the previous section. So it's two ways to see that the answer has got to be 0. With the fundamental theorem in the previous section, using the potential function little f, or using Green's theorem here in this new section. But Green's theorem applies to situations where this vector field is not conservative, where there is no potential function, where the scalar curl is not 0. Green's theorem still applies. Let's do an example of that. The vector field has components mn. What are m and n? They are x plus y and 2x. The curve C, well, initially is described geometrically instead of giving a parameterization. So we got to figure out the parameterization. If you look in the book, it says C starts at 0, 1, follows a parabola to the point 3, 4. Parabola actually looks like this. Goes down first before going up. That'll be C1. This will be C2. C is still C1 plus C2, meaning go along C1 first in the direction indicated, then go along C2 second in the direction indicated. This is still the point 0, 1. This is still the point 3, 4. This parabola is y equals x minus 1 squared. You got to figure out parameterizations. C1, there's infinitely many choices for parameterization. Seems to me the simplest would be to let x be t and let y be t minus 1 squared. Right, that'll be on that parabola y equals x minus 1 squared. T goes between 0 and 3, which if you like, you can expand out the second component to t squared minus 2t plus 1, though you don't have to do that. And C2 is a line segment from 3, 4 to 0, 1. Let's call this R1. We'll call this next one R2. Again, there's infinitely many choices for the parameterization. Since it's a straight line, it's probably simplest to pick a linear parameterization that works as t goes between 0 and 1. That's always the simplest thing to do for a line segment, whether you're in 2 dimensions or 3 dimensions. So for the first component, the x component, notice x goes from 3 down to 0. How is that going to happen as t goes from 0 to 1? Let x be 3 minus 3t. That's how. I'm doing linear equation calculations in my head, right? Pre-calc, that would take them 5 minutes to figure that out. But you just realize, okay, I need a quantity, a linear function of t to be 0 when t is, or 3 when t is 0 and 0 when t is 1. If it helps, draw a graph of such a function. Like that, an ordinary graph in a tx plane. For y goes from 4 down to 1. 4 minus 3t as t goes from 0 to 1. As always, I'll need R1 prime and R2 prime. R1 prime will be 1, 2t minus 2. R2 prime will be -3, -3. The line integral of f over c, which is a closed curve, since c is c1 plus c2, is the sum of the integrals over c1 and c2, which are not closed curves. So you don't need to put the circle on these integrals. Then you use the parameterization. For R1, t goes from 0 to 3. You compute these dot products. For R2, t goes from 0 to 1. Okay, again, f is x plus y, comma, 2x. So we're going to get the integral from 0 to 3. F of R1, where's R1? It's right up here. I need to add x and y. I need to add the first and second components there. Right, I'm plugging R1 into the first component here, x plus y. I need to add them to get the first component of this thing. X plus y. Add these. T minus 2t is -t. I'll get a t squared minus t plus 1. T squared minus t plus 1. For the second component, I take 2 times x. 2 times t. Dot that with R1 prime. I forgot my prime here, sorry. Forgot it there. Dot that with R1 prime, that's this vector, 1 comma 2t minus 2. Add the integral from 0 to 1 of f of R2. Again, the first component of f is x plus y. Look at R2 right there. Add those two things. Get 7 minus 6t. 7 minus 6t. Then do 2x for the second component. 2 times that is 6 minus 6t. Dot that with the velocity vector, -3, -3. Now you got to do the dot products. T squared minus t plus 1, I'm looking right here, times 1 plus 2t times that is plus 4t squared minus 4t. I'm looking at multiplying those two things. That all simplifies to 5t squared minus 5t plus 1. You're always hoping you haven't made a mistake. I'm not guaranteeing I haven't yet. Got to do this dot product. Don't forget my dt there. Negative 3 times that's going to be negative 21 plus 18t. Then negative 3 times the other one's going to be minus 18 plus 18t. That all simplifies to 36t minus 39. Getting close. Started it by hand. I might as well finish it by hand. 5/3 t cubed minus 5/2 t squared plus t from 0 to 3 plus 18t squared minus 39t from 0 to 1. 3 cubes 27, divided by 3 is 9. 45 minus 45/2 plus 3. And then plus 18 minus 39. That's a negative 21. These two are 48. So we get what? 27 minus 45/2. 54 minus 45/2. 9/2. 4.5. I hope I have not made a mistake. Going as quick as I can here. Got a new vector field, which, by the way, this vector field here is not conservative. M and N, it's scalar curl nx minus my is 2 minus 1 is 1, constant but not 0. The double integral of the scalar curl is going to give you the volume, or the area of the region, because you're doing a double integral of 1. Evidently, the area, if I've not made a mistake, the area is 4.5. There's the vector field. R1 of t is t minus, I'll type it like this for sake of emphasis, R2 of t, 3 minus 3t, 4 minus 3t. Okay, let's just type it in all at once here. Integral from 0 to 3 of f of R1 of t dotted with R1 prime of t plus integral from 0 to 1 f of R2 of t dotted with R2 prime of t. The dot is a period. There we go. Got the right answer. How do we do this as a double integral of the scalar curl? Go back to your region there. The d is what's inside. If we think of it as vertically simple as between the graphs of two functions of x, x goes from 0 to 3, and x would be the outer integral. And y goes between these two functions of x. This function on the bottom, what about on the top? It looks like y equals x, 3x plus 1. It's not 3x plus 1. It's x plus 1. There we go. Which is the same then as the area of this region. So in this case, Green's theorem says another way to compute this area is to compute a line integral to get the area. Usually we do a double integral of 1 over the region to get the area. But you can use Green's theorem to find an area, which is another point of emphasis. And you've got homework problems about this. Go back to Green. The area of D, we know from double integrals, that's the same as doing the double integral of 1. But wait a minute, don't double integrals give you volumes? Yes, they do. But in this case, the volume can be interpreted as an area, because it's the volume of the solid under the graph 1 above the xy plane, area of the base times 1, which is the area of the base. Of course, the units for volume and area are different. Technically, the units for the double integral are cubic meters or whatever. but the numerical value is the same as the area of the base because the height is 1. So the area is the double integral, and by Green's theorem, that's a line integral of a vector field around C, where the vector field, again, where the C is oriented counterclockwise. That is important. So you've got a region D, and you're trying to find its area. You can parameterize its boundary counterclockwise. That'll be the C. And this will be true as long as what am I missing from Green's theorem here? The curl of the vector field is always 1. So as long as you choose a vector field whose curl is 1, you can compute the area of a region as a line integral. That is sometimes useful. It might be easier to compute the line integral than to compute the double integral. That does sometimes happen. End class with an example. Say you'd like to figure out the area of an ellipse. Maybe it's the ellipse with equation x squared over 64 plus y squared over 25 is 1. That's going to have x and y, x-intercepts at plus or minus 8, and y-intercepts at plus or minus 5. There it is. It's an oval. What's its area? There is a formula for the area of an ellipse, but you may not know it. If you tried to do this area as a double integral of 1, it's kind of a tricky integral, I believe, involving square roots and stuff. But if instead we parameterize this ellipse using r of t equals 8 cos t for the first component and 5 sine t for the second, as t goes from 0 to 2 pi, that will parameterize that ellipse starting at the rightmost point and going around as t goes from 0 to 2 pi. And if I pick a vector field whose scalar curl is 1, for example, if I pick it to be 0x, for example, that's a simple vector field whose scalar curl is 1. The integral of that vector field will give you the area of the ellipse. What function would you integrate? It would be this function. And if you integrate that function from 0 to 2 pi, you're doing it by hand. There's a trigonometric identity that you can use. You can also do it by parts. You get 40 pi, which is the area of the ellipse. And notice the area of the ellipse is the same as 8 times 5 times pi, where 8 and 5 come from the x and y intercepts. Okay. Doing the line integral is quicker than doing the double integral. So that's one application of Green's theorem. I'd say the major application that will come to the last week or so of the course is really to understand the scalar curl better. Another key feature application of Green's theorem is to understand the scalar curl better. Here we're just using it to either compute a line integral or compute a double integral. It gives you a tool for doing so. That might be easier than doing it directly.